you for joining the webinar today. I'm Dr. Callie Babbitt, and I'm a faculty here in the Golisano Institute for Sustainability. I'll be sharing some of the information about our research in environmental impacts of emerging technologies, specifically a case study on electronics and electronic waste. And I look forward to receiving any questions that you have about this topic. You're welcome to submit those using the chat or question function. And then I'll plan to answer those at the end of the webinar. We have a little bit of time factored in then to start. So I'm looking forward to sharing some of the research today, but I have to first give credit to the many collaborators and students who are involved in this research. Our group includes master's, PhD, and undergraduate students, and even on rare occasion, high school students. And so I've listed several of them here on the slides today. So I first want to mention how the research that we're doing relates to the broader picture of sustainability here in the Golisano Institute for Sustainability. This degree program and research institute is organized around research in sustainable systems, or in another way, knowledge to enable the future sustainability workforce. We offer PhD, masters in sustainability, as well as a Master of Architecture with a focus on sustainable infrastructure. We also do a lot of work with industry and community partners to implement some of the sustainability strategies all the way from theory to application. And a lot of what we focus on are solutions to global challenges like e-waste management. How can we understand resource consumption, manufacturing, energy use, education, and clean recycling and remanufacturing? Electronic waste is a prime example of this topic, and I hope that I can share today some of the research in this area. So one of the hallmarks of the Golisano Institute for Sustainability is systems thinking for emerging technologies. And when I say systems thinking, what I'm talking about is the ability to comprehend the entire life cycle of an emerging technology. So all the way from resources being extracted from the earth, manufacturing them into goods and components, transporting them, using them, and ultimately managing them at the end of life, ideally by closing this loop and returning them into productive use instead of extracting more raw materials. And what we seek to do is understand all of the potential environmental impacts that happen across this life cycle. And there's a pressing reason why we have to shift our paradigm in technology from just looking at how it performs to how it impacts the entire life cycle. Because when we have not done that, we've run into a lot of environmental problems. And I first got interested in this topic because of the issue of electronic waste. This is a classic example of a failure to apply systems thinking in a proactive manner. So let's consider consumer electronics, especially those introduced 10, 20 years ago. They were introduced very quickly. We all purchased them very rapidly, and they had a relatively short lifespan, so they quickly entered the waste stream. The materials are a mixture of very high-value materials that subsidize and encourage recycling, but also potentially hazardous materials. And the example here is shown are cathode ray tube televisions, the big boxy televisions that we no longer purchase, but which are still contained in many homes in the US and around the world. And these contain lead, which of course is a toxic material we're concerned about minimizing impact. Another concern here is that when these products were first being introduced, no one was thinking very proactively about their recycling or their management at end of life. And as a result, the policy and the infrastructure for managing these has always been backwards looking. So the question that I had was, what if we could, instead of being backwards looking, be more proactive and try to avoid future pitfalls when it comes to new technology? And these examples are covered in some of the other webinars that we're sharing here at GIS and other parts of my own research portfolio. But you can certainly think about this in the case of, say, solar panels or lithium-ion batteries, materials for which we haven't yet fully considered the implications of their full life cycle, and we're not totally ready to manage them when they come into the end of life waste stream. And so the goal of our research group is to try to be more proactive, understanding what the potential systems risks are of new technology, and then coming up with sustainable solutions. It's always more cost-effective and environmentally friendly to try to prevent these problems from occurring rather than reacting and introducing solutions at the end of pipe. And the research that I do, along with my students and collaborators here at RIT, has several key examples. So in addition to consumer electronics, which I'll talk more about today in detail, we also think about engineered nanomaterials, lithium-ion batteries and electric vehicles, and more recently getting into new technologies that are being used to manage food losses and waste in order to turn this waste stream into energy and other valuable bio-based products. So consumer electronics are a fascinating example because they have potential for environmental risk all across their life cycle. They use a mixture of materials with high environmental impact or mined from vulnerable regions, as well as base materials and things that are relatively easy to obtain and then recycle. Some of the manufacturing processes use significant material and energy inputs and can create carbon dioxide and other pollutants that potentially harm our ecosystem or human health. At the use phase, there's a lot of really interesting dynamics that are determined by how the consumer uses these products. Many people have increased their use of consumer electronics as these products have become more multifunctional and miniaturized so that they're with us everywhere we go. And certainly, as the lifespan of products continues to shorten and new products are introduced, we also have to then think about their waste management, whether they can be reused, refurbished, or recycled, or if they ultimately end up being disposed of, potentially in a harmful way. So there's a lot of work that's been done in this space, and this slide overviews a few of them. Certainly there's been work in terms of things like Energy Star, which are voluntary programs to label products that meet certain energy criteria. There's new efforts by communities and states at the policy level to create incentives and mechanisms to recycle products. And there's also quite a bit done to think about design and labeling of products so that consumers can understand which ones have the lowest environmental impact when they're making purchase decisions. And as a result of many of these efforts, as well as the natural progress of technology over time, we've certainly seen an improvement. If you look at any single electronic device, the energy that it takes to manufacture it and in use has decreased over time. However, we keep buying more. This is a classic example of what we think of as the rebound effect. The impact of a single product reduces, and in many cases the price reduces, and as a result we purchase more devices. And so the question becomes, how can we think about these products in a new way, especially as we're facing not so much the legacy devices that you're seeing here, like TVs and laptops, but rather new things that we might not have thought about before as electronics, like fitness trackers and smart watches, smart sneakers, and home appliances. There's a whole array of these products coming out, and we don't simply purchase one of them at a time. We buy many of these products, and we buy them in an interconnected and interacting way. For example, you wouldn't likely just purchase a printer. You'd also have a computer with which to create the media that you're going to use the printer to generate in a hard copy format. And so because of this interaction of products, we've seen a significant increase. Now, this graph is sort of a conceptual schematic that shows in the blue circles, the blue power buttons, the average number of products in the average US household over about a 10 to 20 year period. And you can see from 1992 to 2007, the number of products per household increased by a significant amount. And in the bar next to that, the environmental impact of this entire array of products has also increased. Now, 16,000 megajoules, that's about equivalent to 30% of the energy that same household uses in a vehicle in that year. So if you wanted to reduce your impact of a vehicle, you can simply drive less or choose a more fuel-efficient model. But if you want to reduce the impact of your consumer electronic devices, that's a lot of different products that you have to change, either the use, purchasing, or management of. So it's a much more complex system. And we started thinking about models that could potentially be useful to help understand an interacting system. And through a lot of interesting conversations with ecologists here at RIT, we came with the idea of modeling consumer electronics after natural ecological systems. In nature, an ecologist would never study a single species in isolation. They would think about how these different products or different organisms interact, the potential competition or predator-prey relationships between the organisms, and as well as the impact that that causes on the ecosystem as a whole. So those interactions create a given structure of an ecosystem, which mediates the material, energy, and waste or biomass flows through that system. So we said, what if we could take the same concept and apply it to consumer electronics? Instead of looking at one product at a time, can we look at this system as an ecosystem of products that are all interacting together? And so that means we can think about what that structure is, what are all the different devices that are being considered, and the external factors that are driving their adoption and use, such as prices or technological progress. And as a result, think about the material and energy flow and waste generation through this ecosystem of products. So this is a really interesting concept, and we've kind of mined this ecological analog in many different ways. And so some of the approach I want to share with you today has to do with thinking about modeling the net material impact and the waste generation associated with this ecosystem. I'm sure you've read a news article that has said there's a tsunami of e-waste coming. New devices are being introduced. We're buying new phones and products every day. And as a result, there's going to be a huge increase of resource and waste. So we actually wanted to say, is that true? If you look at this entire ecosystem of devices, what is the real trend in resource use and waste generation? And what does that mean for proactive sustainability solutions? So our approach, and which I'll lay out in a few conceptual slides here, was to first try to characterize this technology product ecosystem. So we looked at the average US household and the 21 most commonly owned products from 1990 to 2015. And the first step was really understanding what is the adoption and ownership of these products. For example, how many are there per household, and are they in use or in storage? Next, we characterize the new products that were being purchased every year. So products aren't simply purchased to replace a product. They're sometimes used in complement to each other. And in many cases, I'm guilty of this, as many of you may be as well, we keep products even after we're finished using them. We then looked at how these things changed over time and rearranged and created a mathematical model to predict the potential electronic waste that would be generated because of these changing trends in adoption and ownership. Now, this just gives us information about product sales, ownership, and waste at a per product level. But what's really important is what's inside those devices, how much they weigh, and what that means for a cumulative resource impact. So we did a lot of data collection. So this is a photo of a very comprehensively disassembled device, but there's not a lot of data that exists for consumer electronics in terms of their material characterization at a really, really fine scale. There's a lot of variability as well about how much products weigh and how long they're used for. So one of the characteristics of my research group is that we spend a lot of time really sinking our hands into what these devices are used, how they're used, and what they're made of, and how they're designed. And so many of the students that I want to acknowledge today have spent many hours investigating a wide array of products. This is quite a labor of love. But with this information, we're then able to pull all of these data sources together into what we're calling a cumulative material footprint of this product ecosystem. And I want to share some of the key findings of this as a representative of our research group efforts, and then talk a little bit about what that means for proactive products. So one of the key findings is, as we all suspect, product consumption is in fact growing, but the net material footprint is slowing, and in fact beginning to ebb. The e-waste stream, at least for households, is starting to decline. It's no longer one of the fastest growing waste streams. It is now still a complex challenge to address, but it really is changing in fundamental ways that have strong implications for policy and recycling infrastructure. So the first chart I want to show is a chart that shows the sales of new technology products into U.S. households for over this 25-year period, and this is by unit. So this graph goes up to about 450 million units of products sold into households. And as you might expect, if you can see the gradation that at the top, that's a blue color, and that corresponds with tablets, smartphones, and other mobile devices where we're seeing a lot of growth in those markets. However, at the bottom, you see declines in many of the legacy devices like desktops or large CRT monitors. On the other hand, you see a large increase in flat panel or LCD TVs and monitors. But what's interesting about this is you note that we are starting to see a slowing and possibly even decline of these products in terms of inflow. So part of that is because there's a saturation point for many of them. Part of them is because consumer spending has changed slightly in these areas. And part of them is because some of the consumer electronic purchase is towards new emerging devices not covered by this analysis, which I'll talk about more in a moment. Now, I want to show the same exact inflow, but instead of looking at it by product, instead look at it by mass. So this chart shows the same array of products, but now looking at their contribution to the total inflow or sales into households in the United States by mass. So taking into account their average weights and sizes. So one of the things that's really interesting is you do see a significant increase till about the mid-2000s, which is about midway through the point of the graph. But as you can probably remember, around 2007 and 2008, we were faced with a digital transition in television signals. And as a result, there was a rapid phase out of sales of new cathode ray tube televisions and monitors. And the darker orange color, the flat panel devices, began to be introduced around that time. There's a dip in the late 2000s that corresponds both with the recession and a slight decrease in spending, as well as the fact that the big, bulky, heavy TVs had dipped, and the new, lighter, flat panel TVs had not yet reached their full market potential. But you can see that even when they have, in say around 2010 to 2012, they even began to slow. And a lot of that is because of natural product innovation. So we're replacing larger flat panels with LED models, which are not only lighter, they're also more energy efficient. And many of the products that we purchase in the most amounts are small mobile devices, which, as you can see in the very, very top category in blue, are really not a major contributor by mass. So this is what's coming into the household. So you would expect a similar trend to be reflected in what's coming out into the waste stream, just delayed by a few years, because we keep these products for anywhere from 2 to 10 to even more years on average. And so this slide shows the average weight of the e-scrap or e-waste stream coming from U.S. households, again by mass. Now, this could be products that are going directly into recycling or hopefully not into the landfill, although we know that happens. But it could also be products that are then going into reuse or resale markets. We're not differentiating here. And the same trend is clear here. The e-waste stream is beginning to shrink and slow down, largely in part, largely due to the fact that we're eliminating these larger, bulky legacy products like cathode ray tube televisions and monitors. And we know that many households still have those in storage, about 20 to 30% on average across the U.S., but they're declining. And this is at a national level, but when we talk to policymakers in different states, they're seeing the same trends at a state level as well. So this is kind of a paradigm shift from this ever-growing electronic waste stream. We also were curious about materials of concern in this stream, because a lot of the regulation around electronic waste is motivated by a concern that it's a hazardous material, and if it ends up in landfills, it could cause human or ecological health. Now, I certainly don't disagree with the idea that putting this material in a landfill is not a good idea, because these products have many, many valuable resources that we can extract from the waste stream rather than mining new ores. On the flip side, however, we can see from this trend, the lighter blue line at the bottom corresponds with the lead inflow into households in both the CRT televisions as well as circuit boards that used to use lead solder. The green is the outflow there at the bottom, and so that's beginning to shrink. And the darker line, the larger darker line, is the lead contained in stock. So those are the products that are in households. And this was really interesting to us because lead, again, is this regulatory motivator of recycling, where in fact it may actually be naturally declining. So we have to kind of rethink the motivation and the goal of our recycling programs. On the flip side, the change in material and product composition also has increased some new challenges. So we also looked at, for example, lithium-ion batteries. So we love our lightweight mobile devices because we can take them anywhere. That's because they're battery powered. And those batteries are a challenge that is still confounding our recycling stream. They're somewhat flammable or explosive if handled in the wrong way. They do have some valuable materials, but they also have some material that is not currently being recycled. And you can see that this is looking at the total outflows in metric tons of lithium-ion batteries, what's entering the waste stream from a variety of products, and those are all continuing to increase over time. So this changing consumption at the ecosystem level has some promising results or some natural attenuation of the resource use. On the other hand, it also creates a new challenge. And so how can we use that framework to think more proactively? Because it's not big monitors and desktops that we're purchasing now, it's small devices like smart home security and drones and smart textiles and wearables and thermostats and things that you see here. And these products offer some new innovation. So for example, if you can use a smart thermostat in your home and reduce the energy consumption, that's a huge savings. Is it worth it in terms of the materials and resources you're going to invest to make a traditional non-smart product smart? And so I want to share just a couple case studies that we're working on currently. This graph shows the average mass in kilograms of all of the products that we analyzed in the first phase of work, those 21 most common, and then some of these new emerging products. The darker lines on those represents the uncertainty in terms of what it might be on a maximum and minimum level. So in the larger graph, you see a lot of those legacy products like televisions, monitors, and computers. The little inset graph is just a magnification of the far right-hand side of that axis, and that's where you actually see a lot of these new devices like the thermostat, the fitness tracker, and the drone. So one of the things that we're seeing is that a lot of the products we're purchasing now that are emerging are small compared to legacy devices. That doesn't mean they're without challenge. So let's take a look really quickly at one of the examples we're studying, and that is fitness trackers. And again, these are products that we've studied, and the research here is led by our wonderful students in sustainability. So we have a few images here of some common fitness trackers. Here's one that you wear, and here's another that you clip on. One thing that you may be noticing in these is to actually disassemble them to obtain the material inside. We're seeing a lot of destruction. This is telling us that these products are not very repairable, they're not recyclable, and there's new materials. Most of them have rubber, which is not a material that we're currently recycling in the e-waste stream. So the lesson here is that smaller is not necessarily better in all sense. We're reducing resource consumption, but we're also introducing new recycling challenge, much more complex. Our old mentality of disassembling products in order to recycle them or repair them is no longer applicable, and the new materials aren't necessarily feasible in our current recycling infrastructure. Another example that we look at is smart home products, and one case study here is smart thermostat. So again, we have a beautiful image of a very common smart thermostat, and we compared its material footprint to that of what we might consider a representative non-smart thermostat, or one that doesn't have the additional capabilities for sensing and learning and calibration over time. And in most of the cases, making these products smart adds very little resource use or environmental impact. They already have some electronics in it, and the amount that you're adding was relatively small. So this graph compares cumulative energy demand, which is the embodied energy of material production. It's kind of a proxy for the environmental impact of producing all of the materials required to go into these devices. And you can see that it's almost negligibly different between the smart thermostat and the non-smart thermostat. The big difference is that we're changing the battery system from from alkaline to lithium-ion battery, and we're also adding some additional display and other products. But it's relatively small, which suggests that if we're going to think now about smart devices, we have to really understand the marginal contribution that adding these additional materials and capabilities can provide. So this is just hopefully a quick snapshot of some of the work in electronic waste we're doing, and I hope it's helped to underscore this concept that systems thinking is necessary if we want to avoid the unintended consequences that often come about if we introduce new products or technologies without fully considering their life cycle. And we use a wide array of these methodologies like life cycle assessment or material flow analysis, which I showed an example of today, to understand the issues around emerging technologies so that we can be more proactive about new technology design. And we can also think about what this means for things like education of consumers, policy, and other ways of getting this information and putting it into practice. So this is, again, just a snapshot. The 2 bits of the study that I shared today are available in reports that are downloadable at this web address. And I also provide my contact information here. Please feel free to get a hold of me by email if you are interested in taking a look at some of these reports in more detail. And certainly we've published a lot of these in peer-reviewed context. But this is just a quick overview. Excuse me, a quick overview to share with you today. And I certainly, again, really want to underscore my acknowledgement and thanks to the many students and faculty collaborators who've made this research possible, as well as several of our partners like the Consumer Technology Association, Staples, and the National Science Foundation. I'd love to connect on Twitter or on email and would be happy to share more of this information over time.